the initial height should be 15 meters, and the initial velocity should be 10. And for acceleration, I'm going to use minus g, and to keep life simple, I'm going to call it minus 10. As you know, the correct answer is 9.8, but we don't want to use the calculator now, so we'll call it minus 10. Consequently, for this object, the position y at any time t is known to be 15 plus 10t minus 5t squared. That is the full story of this object. Of course, you've got to be a little careful when you use it. For example, let's put t equal to 10,000 years. What are you going to get? If you put t equal to 10,000 years or 10,000 seconds, you're going to find y is some huge negative number. Now, is that right, or what's wrong with that reasoning? So you cannot use the formula once it hits the ground, because once it hits the ground, the fundamental premise that a was a constant of minus 9.8 or minus 10 is wrong. So that's another thing to remember. Once you get a formula, you've got to always remember the terms under which the formula was derived. If you blindly use it beyond the validity, you will get results which don't make any sense. Conversely, if you get an answer and it doesn't seem to make sense, then you've got to go back and ask, am I violating some of the assumptions? And here you will find the assumption that the particle had that acceleration is true as long as it's freely falling under gravity, but not when you hit the ground. Now, if you dug a hole here till there, then of course it may work till that happens. Okay, but you got to know every time when you. This is so obvious in this problem, but when you see a more complicated formula, you may not know all the assumptions that went into the derivation, and quite often you'll be using it when you shouldn't. All right, see, this, you agree, is a complete solution to this miniature, tiny Mickey Mouse problem. You give me the time, and I'll tell you where it is. If you want to know how fast it's moving at a given time, if you want to know the velocity, I just take the derivative of this answer, which is 10 minus 10t. So let me pick a couple of trivial questions one can ask. One can ask the following question. How high does it go? How high will it rise? To what height will it rise? So we know it's going to go up and turn around and come down. We're trying to see how high that is. So that is a tricky problem to begin with, because if you take this formula here, it tells you y if you know t, but now we are not saying that. We don't know the time. And we don't know how high it's rising, so you can ask, how am I supposed to deal with this problem? Then you put something else that you know in your mind, which is that the highest point is the point when it's neither going up nor coming down. If it's going up, that's not the highest point. If it's coming down, that's not the highest point. So at the highest point, it cannot go up and it cannot go down. That's the point where velocity is 0. If you do that, let's call that particular time t star, then 10 t star minus 10 is equal to 0, or t star is 1 second. So we know that it'll go up for 1 second, then it'll turn around and come back. Now we are done, because now you can ask, how high does it go? Then you go back to your y of 1, and y of 1 is 15 plus 10 minus 5, which is what, 20 meters. By the way, you will find that I make quite a lot of mistakes on the blackboard. You're going to find out, one of these years when you start teaching, that when you get really close to the blackboard, you just cannot think. There's definitely some inverse correlation between your level of thinking and the proximity to the blackboard. So if you find me making a mistake, you've got to stop me. Why do you stop me? For 2 reasons. First of all, I'm very pleased when this happens, because I'm pretty confident that I can do this under duress, but I may not do it right every time. But if my students can catch me making a mistake, it means they're following it and they're not hesitating to tell me. Secondly, as we go to the more advanced part of the course, we'll take a result from this part of the blackboard, stick it into the second part, and keep manipulating. So if I screwed up in the beginning and you guys keep quiet, we'll have to do the whole thing again. I would ask you, when you follow this thing, to do it actively. Try to be one step ahead of me. For example, if I'm struck by lightning, can you do anything? Can you guess what I'm going to say next? Do you have any idea where this is going? You should have a clue. If I die and you stop, that's not a good sign. Okay? You've got to keep going a little further because you should follow the logic. So, for example, I'm going to calculate next when it hits the ground. You should have some idea how I'll do it. Because this is not a spectator sport. If you just watch me, you're going to learn nothing. It's like watching the U.S. Open and thinking you're some kind of player. You will have to shed the tears, and you've got to bang your head on the wall, go through your own private struggle. I cannot do that for you. I cannot even make it look hard because I have memorized this problem from childhood. So there is no way I can make this look difficult. Okay, that's your job. All right, so we know this point at 1 second is 20 meters. So let's just ask one other question, we'll stop. One other question may be, when does it hit the ground and with what speed? A typical physics question. So when does it hit the ground? Well, I think you must know now how to formulate that question. When does it hit the ground is when is y equal to 0. By the way, I didn't tell you this, but I think you knew that I picked my origin to be here and measured y positively to be upwards, and I call that 15 meters. You can call that your origin. If you call that your origin, your y0 will be 0, but ground will be called minus 15. So in the end, the physics is the same, but the numbers describing it can be different. But you have to interpret the data differently. But the standard origin for everybody is the foot of the building. You can pick your origin here, some crazy spot. It doesn't matter. But some origins are more equal than others because there are some natural landmark there. Here, foot of the building is what I call the origin. So in that notation, I want to ask, when is y equal to 0? So I ask when y is equal to 0, then I say 0 is 15 plus 10t minus 5t squared, or I'm canceling the 5 everywhere and changing the sign here, I get t squared minus 2t minus 3 equal to 0. That's when it hits ground. So let's find out what the time is. So t is then 2 plus or minus 4 plus 12 over 2, which is 2 plus or minus 4 over 2, which is minus 1 or 3. Okay, so you get two answers when it hits the ground. So it's clear that we should pick 3. But you can ask, why is it giving me a second solution? Anybody have an idea why it's, yes?
Because if there was an entire parabola that started from y equals 0, it would have been negative.
That's correct. So her answer was, if it was a full parabola, then we know it would have been at the ground before I set my clock to 0. So first of all, negative time should not bother anybody. T equals 0 is when I set the clock. I measure time forward, but yesterday would be t equal to minus 1 day, right? So we don't have any trouble with negative times. So the point is, this equation does not know about the building. It doesn't know the whole song and dance that you went to a building and you threw up a rock. It knows nothing. What does the mathematics know? It knows that this particle happened to have a height of 15 at time 0 and a velocity of 10 at time 0, and it is falling under gravity with an acceleration of minus 10. That's all it knows. If that's all it knows, then in that scenario,